Hi, I'm Rich with Inside HPC. We're here at the Intel HPC Developer Conference, and I'm here with Simon Warfield from the Boston Children's Hospital Medical College, part of Harvard Medical School, is it not? Yeah. Well, let's start at the beginning there. What is the nature of your work there?
So I work in the radiology department, and I work with different clinicians at the hospital, trying to understand how different imaging questions that they have can be addressed by my research group.
And what are the challenges associated with that as far as computation?
So radiology is becoming increasingly quantitative. Today MRI scanners don't just take pictures, they acquire data that needs to be interpreted quantitatively. And so we solve mathematical questions in order to derive information and data from the images which are being made by the machines.
And how is Intel helping you with that process?
So some of the measurements that we make are very computationally intensive to interpret, and Intel is providing us with the necessary hardware boost to be able to do things, to answer those questions as quickly as we need to.
So Simon, now that we're not just doing film, is this like 3D, 4D? What's the nature of this work?
So in some of our work, we're trying to understand the neural circuits in the brain. And to do that, we require MRI data that probes the brain in 3 dimensions in space, but also the microstructure of the brain, adding a 4th dimension. And in order to understand the tissue compartments which are present in the brain, we have to solve an inverse problem. So we turn the 4-dimensional measurements into a model of the internal microstructure of the neural circuits. So it's a very computationally expensive inverse problem. We're able to use Intel's hardware and compiler technology to accelerate that process.
And being patient care, I mean, there's a timeliness involved here, isn't there?
Absolutely, yeah. So we've used that approach for planning for surgeries, where we want to understand what are the circuits in a particular individual's brain. But we've also used it to develop imaging biomarkers to predict longer-term outcome. So we've been using this technology to look at the question of who will later develop autism spectrum disorder. And we're starting to find changes in the white matter microstructure that help us understand what the later outcome will be for those children.